Okay, so we left off last time with free body diagrams, which are really just drawings. They're drawings of your object with the forces acting on them. And so it's helpful so you know exactly what forces are acting on the object you're talking about. Like, we'll go over the elevator in an example, and you can just sort of isolate just the object itself that you are dealing with. So a book sitting on a table, just draw the object. We've actually done these before in 9th grade. We'll do a few more drawings, just like in 9th grade. There's my book. I don't even need the table, just draw the object. That's the whole free body idea. What forces are acting on the book? The force of gravity, which is going to be the book's that's there too. The force of gravity on an object we are going to call the weight of the object. Okay. And we're drawing these as vectors. So, try to draw them to scale. If the book is not crashing through the table, then this would be, an inappropriate drawing. Try to make the force up the same size as the force down. So weight's pulling it down, and you were right, normal force pulling it up, pushing it up. And if it's balanced, it'd be nice if they looked like they were the same size. Maybe. The end. So vectors, so put the arrowhead on there so you can easily look at your picture and know what direction those forces are acting in. All right, how about a baseball flying through the air, bearing in mind that there's no air in AP Physics?
Weight.
Yeah, weight. Pretty much always put weight on something. Well, if it's flying through the air, shouldn't there be a force like to the right or left?
Right. We don't.
Yeah, it's velocity. Okay, it's going this way. Do I just stick on a V for velocity force? Don't be writing that. No, it's going this way because somebody hit the baseball or somebody threw it originally. There definitely was a force to get it going that way. But if it's not attached to the bat or attached to somebody's hand, that force is gone. That force is no longer acting on the ball. So that's actually it. Just weight. It's not on the ground. There's no normal force. All right, technically you probably would put air resistance on there, but we're going to leave that off. If I want to do baseball now when it's hit by a bat, sure, I would need another force there. Still have my weight. It's a really big baseball. And this is where you can sort of just label it however would make sense. F bat, FB.
With the force of
I don't know, how hard was it hit?
That's what I was saying.
Yeah, likely it would be much bigger, you're right. There you go. You're right, I shouldn't talk about scale and then draw. Maybe it was just bunted. Okay, so we'll come back and draw a few more of these free body diagrams. But let's mention elevator problems for a second. We were talking about elevator problems yesterday. If you're drawing a free body diagram for a person in an elevator, you would just draw the person. And like we said, yes, there's definitely a cable pulling the elevator up, but is the cable attached to the person? No. As far as what's acting on the person, it's his weight and the floor. The floor is pushing him up. So we would only use the end. Now, at certain points when you're riding an elevator, you may feel like you weigh more, like you're heavier or lighter. Of course, it's not because your weight changed, but it's because the normal force changed. And that's often called your apparent weight. So I want to draw free body diagrams just for a person in an elevator. So the free body part is just going to be the guy. as a stick figure. Okay, so on this guy, start at the bottom. If he's at rest on a ground floor, what should our free body diagram look like? Weight pushing down and normal force pushing up. But how should the normal force compare to the weight? Exactly equal. Good. It's balanced. We're at rest. All right. What about now we're speeding up? The elevator is now accelerating upward. You feel that little jolt in your knees. Weight pushing down. Does the magnitude of the weight change? No. It should still be the same size. It should be for all of these. Despite that it might feel like you weigh less, you don't weigh less in an elevator.
The weight is mass times gravity.
Or more.
And if it's accelerating up, wouldn't that mean that the gravity, like I don't understand my weight.
The weight is the same. Now the net is the combination of your weight and your normal force. So if you wanted to know your net acceleration, you would have to compare both of them. But as far as your actual weight, gravity is still gravity, mass is still your mass. So the weight would always be the same. Okay, if you're speeding up, going up, how does the normal force compare to the original normal force? It's bigger. If you're speeding up, the upward force has to be bigger. And this is where it would look like you weigh more. Should have that little dial turning. Now we've reached a constant speed. Maybe it's a really tall skyscraper, so we're going to go along at a constant speed for a while. What would the normal force look like here? Good, equal. It's not gone. It's not less. It's now equal to the weight. And then we reach a point where we... So how would the normal force compare there? It would be less. And if this situation continued over however much time, according to our picture, weight's going to win out and this thing will ultimately go down. It's like this person wants to go downward because the downward force is bigger. So if it was going up already and our downward force is bigger, where those directions don't match, that was our slowing down example. Okay. So we're drawing free body diagrams, just drawing the object and the forces acting on it based on the little scenario that it says. So, a box being pushed straight across the floor. There's a box. Now what? Okay, I've got weight down. What else? Normal force pushing back. What else? Yeah, being pushed. And I'll call that F push. And not that we've gotten into this in chapter 5, but we will use a lot more in chapter 6. Friction, which would go which way? Good. Opposite the way the object is moving or sort of wants to move. Yeah. Well, depends on what I've told you, what other information I've told you. It doesn't say necessarily constant velocity. It doesn't say it's accelerating. So I'm just going to make it equal for the time being. Call that force of friction. Capital F, little f. Sometimes we even would stick a K on there for kinetic friction, but we'll get to that later. FF for friction. So now that I've got a good picture, and you're right, I don't necessarily know which force was supposed to be bigger. Is it slowing down? Is it moving at all? Is it accelerating forward? But given these conditions, I want to come up with some equations that would be true. So a lot of, you do need to memorize quite a few equations in this class, but especially in the forces unit, you've got to be able to come up with your own that apply to each particular problem. So I want you to come up with an equation that's true, based off your picture, if this box is moving at constant velocity. Not all of them are equal, but which sets are equal? Okay, so I would definitely know weight equals normal force. That's going to be true regardless, so long as it's not crashing through the floor or flying off the floor somehow. Yeah, and this would be true too. Force of friction would have to equal the push force. If it's moving along at a constant velocity, those forces have to be balanced. Now, what if it's accelerating?
Weight.
Which way is it accelerating?
Across the floor.
Presumably the way you're pushing it, but good question.
F equals.
Friction is going to be smaller than.
If it's accelerating, I want to deal with F equals, well, not F equals ma, but I want to deal with F net. So if it's accelerating, there is a net force. Now here's always some confusion I see. The net force, it's not like it's an extra force. It's just the sum of what you have. So the net force, this is just an equation you can come up with. In this case, assuming the push force is greater, would be equal to what? Very good, minus friction. So F push would be our big force, sort of the one that's winning out. But friction is not helping. Friction's acting the other way. So minus friction. And then these two would still be equal. So I'm going to leave that off. I'm just going to stick with the net force here.
We have to say that push is greater than that of friction.
You don't have to say it. I mean, it's kind of assumed. But here's something that I do that other textbooks do a little differently, is I use my picture to figure out like what's bigger. Some books will just say, well, add them up, right? F push plus FF, but then you would have to know that FF is negative because it's the other way anyway. So it's kind of the same thing. But I always pick the bigger forces, the forces that are winning out, and I subtract forces that are acting the other way. And then I know from my picture which way that's going. So for my picture, I know we're going to the right. So a good picture will solve all your problems. All right, a car that's braking. Let's try the next one. And we'll put the front windshield in here so we know which way we're going. Okay, we got weight and normal. And a braking force, which, okay, again, here, I know that the braking force has to do with, the brake pads pushing up against the tire, and you ultimately, you originally pushed the brake pedal. But what about the car is allowing you to brake? Friction. If there was no friction, it wouldn't matter if you stepped on the brake pedal. It wouldn't matter if the brake pad was pushed up against the tire. If it was icy, you'd still be going. So friction is the force that is slowing this car down. And the way I've drawn it, if it's going forward to the right, friction's got to be to the left.
Do you need to draw it going forward to the right?
No. And don't do that. Don't try to throw in extra vectors, because that will probably only confuse you. Like, don't throw in a velocity vector on a force diagram.
Are you talking about like the force of friction between wheels and the ground? Or like
Yes. Specifically that force. Okay.
We don't need to add anything. The forward direction's going now.
No. Right. If you're braking, that's it. Now, interestingly, which force also allows you to go? Like go forward? Friction. Friction helps us brake. Friction helps us move forward in our car. Because if it wasn't there and you were in a mud puddle, you would just spin out. So a little aside here. So imagine you're going forward. So like your wheels are turning this way. All right, so imagine a point of contact between your wheel and the ground. Well, which way does one little piece of rubber, one little rubber molecule in your tire want to go that's spinning like this? How about right at this point? Backwards, left. Like this would be like the tangent. Spinning, spinning, spinning. I'm just talking about this one spot where it's in contact with the ground. It's like that little piece of rubber is trying to go that way. Well, friction opposes motion, which will be why friction gives you a forward force. Same with how you walk. If there wasn't friction, we wouldn't be going anywhere. Michael Jackson could do this a lot better, but your foot's trying to go backwards. Okay? Friction opposes the motion that way and pushes you forwards. So friction does oppose motion. All right, so friction is why we can stop and why we go in a car or walking. Obviously, it wouldn't make sense for me to pick a constant velocity example here since it's clearly decelerating, slowing down. So the net force is simply equal to what here? Friction. Yeah, I'm going to try to keep drawing the rest of this page, just a couple more on this page. All right, now, with the box, with incline problems, we usually do draw the incline so we can get that angle. But you're right, we could have just imagined the box on our incline. But all right, a box on an incline being pulled up the incline with a rope. So I am going to draw the incline. But I'm focusing on the box. What are the forces acting on the box, and specifically, which direction do they go? Okay, I've got a pull force along the incline. But if it says rope, what would be maybe a better way to label that? Okay, tension. What else I got?
Weight going straight down.
Good, weight going straight down. And here's where we're going to want to break that into components so that we can come up with these nice little equations. Do you remember what components I told you you'd want? It's not really x and y, it's a tilted scenario, but good. You're right. So this was weight, sorry. And I usually draw weight perpendicular first. So, make sure that is perpendicular to the incline. And then weight parallel is parallel to the incline, not the bottom of the incline, the slanted part of the incline, which would have to make sense if you wanted to fit a right angle in there, which was the point of doing this. All right, and realize again, just like in projectile motion, if we were given that at launch speed and we broke it down into components, we probably didn't use that original launch speed anymore. So once I've found my components of weight, I'm unlikely to use weight itself anymore. All right, but keep going with the forces. Are there any more? Normal force. Which way? Good. Not straight up. A surface can only push, out from itself. So normal force is also perpendicular. That is what normal means in math. To our surface. And I'd like one more. Which way? Good. Opposite the way it's going. This is a good diagram. We've got everything we need on there. So now let's say this box is moving at a constant velocity. What equations can I come up with that would be true? And I would like two sets, for each perpendicular direction. Okay, so
What is the friction?
more. Let's start with tension. Tension sort of up and to the left, right? Is there anything else up and to the left? No. So it's got to balance everything opposite it, which is friction.
Weight parallel.
But good, don't forget weight parallel. Weight parallel is also trying to push this box down the incline. So plus weight parallel. All right, so that was this direction. Now I need to analyze the direction perpendicular to that. So what else would be true?
Normal force equals weight.
Perfect. All right, now I'd like my F net equation. Now we're going to assume it is accelerating, and specifically up the incline. So this person with the rope is winning out. So how would you write that? Okay. F net's largely due to tension, but what is not helping?
What well, minus F and W.
Good. Weight parallel and friction are working against tension. So minus both of them. You could do it in parentheses, or you could distribute your negative sign, but however you want to do it. That is a good F net equation. All right. Move a little faster. I'm going to just try to finish these two, and I'm going to give you some time to work on the last two, or last side. There's a whole other side. Okay, a sled dragged by a rope that makes an angle with the horizontal. So there's my rope. All right, forces. Tension. What else? Weight. What else? Normal. What else? But maybe not that big. Which way? Very good. Perfect. Now, which one of these forces looks a little different? Tension. Tension's at an angle. That makes us sad, but we can deal with it. How? Yep, do your components. And since this is, it's not on an incline, it's perpendicular, parallel perpendicular to the ground, I would go back to x and y. So I call it tx and ty. Exactly. Yeah, you can't shuffle with me. Okay. Wes, tell me an equation that would be true if this sled is moving at constant velocity.
I got TX.
Bigger. Come on, pen. Good. Okay, left equals right. Tx is to the right. Friction's to the left. Perfect. They would have to be balanced if we're moving at constant velocity. Erica, give me the equation for the up and down direction.
Weight equals normal and ty.
Very good. Weight's down, so it's got to equal everything up. Equal normal and ty. Brandon, can you give me the net force if the sled is accelerating? An equation for the net force. And that's it. Perfect. One more time, F net, it's not an extra force that I could add to my picture or anything. It just is the overall force in the direction that you're accelerating in. It's just the resultant. It's not an extra thing. It's just the resultant of what you have. And then last but not least, at least for this side, sometimes you'll have something like a sign hanging by wires, like in this case. So a sign held up by two wires that meet at a point on the sign and form an angle with each other. Like old-fashioned TV. Emily, what forces would I have?
Weight.
Gonna have the weight of the sign. What else?
Tension.
And if we have two of them, or two ropes, T1, T2. And what should I do with those tensions, since they are at angles? Find your components. Now, if this were symmetrical, presumably it is, but if it is symmetrical, then they're equal anyway. T1 would equal T2, but I'll keep them separate. So T2x, T2y, and over here we'd have T1y, T1x. Okay, a little messy. And it would really just have to be still, unless we eliminated the tension, maybe it was falling. But Connor, can you give me the two equations that would have to be true for this to be still?
W is equal to T1 plus T2y.
Good. Make sure you got the y's on there. So the weight down equals everything up. There's T1y, T2y. And what else will be true?